Here I have a seemingly very challenging series, and we're asked to compute it. It says, what's the series as k goes from 0 to infinity of pi cosine pi k times quantity negative sine squared of arc cosine of root pi over 6 to the k power. And now this looks horrifying for most, but I'll show you that it's not really that bad at all. It's really not that bad. And I will show you three methods of how to solve this. The first one being the one that I used when I first created this problem myself, and then the other two more recent that are a lot far simpler and more elegant at the same time. So let's begin. We have a constant pi in here, which means we can really take that out. So we can take the pi out of the sum, or of the series. So if pi times the sum as k goes from 0 to infinity of cosine of pi k. Now, let's look at pi k in the discrete sense with integers. So we have cosine of pi k, and we're going to look at what happens to that value as k is going to increase as an integer. So when k is equal to 1, cosine of pi is negative 1. When k is equal to 0, cosine of 0 is 1, right? When k is equal to 2, cosine of 2 pi is the same thing, 1. So as you can see, with every integer of k, we seem to be just jumping 180 degrees like this forever and ever. Which means that for the sake of this problem, cosine of pi k is equivalent to saying negative 1 to the k. So we can rewrite this now, and that's exactly what we're going to do. So this becomes the sum as k goes from 0 to infinity, and don't forget the pi in the front, of negative 1 to the k, but now we have this term here. And what can we do here? Well, look, we have a negative in front of the sine squared term, so we can take that negative 1 out and say it to the k. Because remember that quantity ab to the k is equal to a to the k times b to the k. So negative 1 is like our a here. And now what happens with these negative 1s is that we're going to use the reverse of that property, and we're going to join them together. So we have negative 1 times negative 1 all to the k. And that just becomes 1 to the k, which is 1 at all times, so we can get rid of that. And now we're simply left with sine squared of arc cos, I'm going to write a cos for short, of root pi over 6 quantity, and then that all together to the k. Now, I'm going to call this entire expression here r. So it becomes the pi times the sum of k going from 0 to infinity of r to the k. Why do I do this? Because then we can use the theorem that says that the sum of the first n terms of a geometric series, so sum as k goes from 0 to n minus 1, of a naught, the initial value of the sequence, times r to the k is equal to that same value a naught times 1 minus r to the power of n, so n plus 1 higher than this, over 1 minus r. And there's a couple of really cool proofs on how to do that. But again, are we going to plug this entire expression in? What do we do with the sine squared of arc cosine of root pi over 6? Who knows? So I'm going to show you what we do. So we're going to consider the value of root pi over 6 itself. What is it? So we know that pi is about 3.14, right? And divide that by 6 is going to be approximately 0.52. So that's pretty close because it's about so 0.52 times 6 is about 3.12, so we're close enough. And now we're going to approximate the square root. What is that equal to? Well, 0.52 is the same thing as saying 52 over 100, right? So taking the square root of that, we can see that the square root of 52 divided by 10. Now note that 52 is between 49 and 64, the perfect squares that are of 7 and 8. So that we know that this value is somewhere between 7 and 8, and since it's closer to 7, we can say that this entire expression is about the same thing as, let's just say 7.2. So we get 0.72, about. That's just an approximation for root pi over 6 alone. But now we're going to take the arc cosine of that, which is what we're being asked. So arc cosine of about 0.72, what is that approximately equal to? Well, let's take a look at our unit circle. So now we're going to use the unit circle, our best friend, to see what it's going to be equal to. So we know that arc cosine is an angle. We know that because arc cosine is the inverse of cosine, whose domain is angles, which means that the range of arc cosine is going to be an angle. So 0.72 is about 3/4, so about over here is our point. And so that's the x-coordinate over here, this value right over here. And so the corresponding angle to it, we're going to call x. We can see that it's between pi over 2 radians and 0. So 0 is less than x is less than pi over 2, right? Because we know that it's not going to be equal to pi over 2, because then arc cosine pi over 2 is 0. And we know that it's not equal to 0. So what we're going to do is we're going to take the sine of this. And why are we taking the sine of this? Because we have sine of arc cosine, but then we square that. So we're going to do sine of the x, as we can see, is not going to be 1 because it's strictly less than pi over 2, but it's also not going to be 0 because it's greater than 0. So we know that 0 is less than sine of x is less than 1 because sine of pi over 2 is 1. And nothing changes with sine squared. When we square that, we still get between the bounds of 0 and 1. But why is this important? So remember that this is our value x. So why is this important? This is important because if sine squared x is between 1 and 0, that means that it's close to some fraction value p over q such that q is greater than p. And I'll explain why this is important when we interpret it in the formula of the series. So we're going to plug this r into the series. And so by that theorem of the sum of the geometric series, we get that sum, right, I'm just going to write sigma here just for sum, is equal to pi, our starting value, times 1 minus r to the n over 1 minus r. And now notice that r to the n has to be a limit as n goes to infinity, because it's an infinite series. And so what happens to r to the n? Well, we just said that r, that sine squared of arc cosine of root pi over 6, which we said is x, so sine squared of x, it's similar to p over q, where q is greater than p, which means that if you take both of those to the nth power, p to the n versus q to the n, because q is greater than p as a base, it's going to grow at an exponentially faster and higher rate than will p, which means that it'll dominate that term, and this entire expression will go to 0 as n goes to infinity, which means that we can take this entire r to the n, the limit as n goes to infinity, and turn it into 0. So we're done with the limit. So the sum that we have from the beginning is now equal to pi times 1 over 1 minus r. And now we're going to expand r to sine squared of arc cosine of root pi over 6. But we know by the Pythagorean identity that 1 minus sine squared x is equal to cosine squared x. So this is the same thing as pi times 1 over cosine of arc cosine of root pi over 6 quantity squared. And of course, cosine and arc cosine will cancel out, so we get root pi over 6 squared. So this is equal to pi times, so root pi over 6 squared is going to be just pi over 6, which is going to be pi in the denominator stays and 6 flips up because it's in the denominator of a denominator, so it becomes 6 over pi. And so these two values cancel out, and we get the beautiful final answer of a nice solid 6. And that's the answer to the question. The answer to the sum as k goes from 0 to infinity of pi cosine pi k times negative sine squared arc cosine of root pi over 6 quantity to the k is equal to 6. Now I'm going to show you a more elegant solution. And we're going to start it the same way. We're going to take pi out, and we're going to turn cosine of pi k into negative 1 to the k, and we'll get rid of that negative and the negative here. And so we know that we have the same setup of pi times the sum of k going from 0 to infinity of sine squared of arc cosine of root pi over 6 quantity to the k. Alright, so now we want to find a more elegant way to express sine squared of arc cosine of root pi over 6. So we're going to take advantage of the fact that arc cosine is actually an angle. So what are we going to do? We're going to say let phi equal arc cosine of x, of some random value x, which means that when we take the cosine of phi, we can take the cosine of the arc cosine of x, which just equals x. And setting up a little right triangle here, we can see that if we put phi over here, that's a horrible right triangle, I'm going to redraw that. Here we go. So we have phi, and we have a right triangle here. So the cosine is going to be equal to x. Now the cosine, again, is adjacent over hypotenuse. So if we let the hypotenuse be 1, then the adjacent x, then cosine of phi is equal to x. What is this remaining side, though? By Pythagorean theorem, this is supposed to be the square root of 1 minus x squared. Because x squared plus this squared, which is 1 minus x squared, should equal 1, and we do get that. Anyways, now, because phi is the arc cosine of x, we can now take the sine of phi to get the sine of the arc cosine, right? And that's going to be equal to just root 1 minus x squared, because it's opposite over hypotenuse. And when we square that, we eliminate the square root, and we simply get sine squared of phi is equal to 1 minus x squared. So we just found a way to express sine squared of arc cosine of x. It's equivalent to saying 1 minus x squared for angles between 0 and pi over 2. And now we just plug in our x to be the root pi over 6, which we know from the last example is a value between 0 and pi over 2. So 1 minus the square root of pi over 6 squared is just 1 minus pi over 6, which is equal to 6 minus pi over 6, just because you try and separate this fraction, you get 1 minus pi over 6. So this is our closed form expression for the common ratio, r, which is amazing. So now we can say this is equal to r, and now the sum is the same. We have the sum is going to be equal to pi times 1 minus this expression, 6 minus pi over 6 to the nth power, divided by 1 minus, and now I'm going to leave it in this form, 1 minus pi over 6, because it's a lot easier in the denominator. And now we know that if we take the limit as n goes to infinity of this expression, right, 6 minus pi over 6, what is that? Well, we know that pi is about 3.14, and 6 is greater than that, which means that 6 minus pi is going to be about 2.9, and that's less than 6, which means that when you take 6 to the n, that's going to grow at an exponentially faster rate than the top, which means that, again, as n goes to infinity, this bottom term dominates, and this expression goes to 0, which is just the same reason we used in the last example. And now we can take the limit out because we solved that. And now we're left that the sum is going to be equal to pi times 1 over, and expanding this negative 1, we have 1 minus 1 plus pi over 6. And these cancel out, of course, and we're left with the same beautiful answer of pi times 6 over pi, which becomes 6. And there you go. We just provided another way to solve the problem a lot more elegantly using right triangle trig and trying to find the closed form expression of sine squared of arc cosine of root pi over 6 so that we don't deal with these ugly looking trig functions. But all along, we've been using an identity that makes this question even easier. And now I'm going to show the third solution, which is the easiest of them all. And the reason I show it last is because it's showing you how you can refine your thinking over and over again the more you try and solve a problem to find better solutions each time. That's exactly what happened with my experience solving this problem. Recall that we're using the Pythagorean identity at the bottom here when we take 1 minus sine squared of arc cosine of root pi over 6. We could have done that all along. So if we reproduce this problem and we have the same setup here, which is essentially this, where we have that sine squared of arc cosine of root pi over 6, watch what we get. So remember, sine squared of x, all right, I'm just going to say that this value is x, right, plus cosine squared x is equal to 1, okay? Which means that sine squared x is equal to 1 minus cosine squared x. And what is x? Well, in this case, x is arc cosine of root pi over 6, which means that this is equal to 1 minus cosine of arc cosine of root pi over 6, all of this together, squared. And of course, now, really easily, we see that these cancel out, and now we're just left with 1 minus, and root pi over 6 squared is going to be pi over 6. So we have 1 minus pi over 6. And now you can see that this setup is the same thing we got here, 1 minus pi over 6. So this is an even faster way of doing it, just using the Pythagorean identity. So essentially, all you're doing to solve this problem, which is equal to 6, as we just said, is you're just using two ideas. You're using the idea of the Pythagorean identity of sine squared x plus cosine squared x equals 1, and you're also using the sum of the geometric series. So you only need to really know two different formulas to solve this scary looking series. And that's amazing to me. And this is why I have so much fun creating a problem like this and going over it over and over again to solve it in different ways. So anyways, I hope that you've seen the differences between these methods and how my initial method involved loose approximations, which still gave us the right answer, while the last two methods used right triangle trig and trig identities to create a more sophisticated and justified answer. So I hope that you have a bit more appreciation for series, for trigonometry, and in fact, if you want to know more about how right triangle trig works with expressions like sine squared of arc cosine, then please check out the YouTube video that I have on Josh Academy involving this exact topic. So I hope that you also have some more appreciation for series and for ingenious thinking like this. Till next time.